Okay, we have seen that the cyclin-Cdk complex, which is the MPF, is controlled by transcription and translation of the cyclin and then degradation of the cyclin. So the reason that M-cyclin is not active here in the S phase is the level of the cyclin is too low in the S phase. Okay, this is a level of control. But unfortunately, this is not enough. Transcription translation plus protein degradation, yes, it is good, it is required. But we know that the cell cycle control must be very sharp. There must be a very sharp passage from one stage to the other stage. It must be very certain. So for this, we must have other kind of controls. So another control comes from the post-translational modifications. This cyclin CDK complex, actually the CDK is phosphorylated by this inhibitory kinase V1. Okay, the inhibitory kinase V1, well, most of the time, all the examples we have seen so far, the phosphorylations were activatory. When they are phosphorylated, they were active. This time it's the opposite case. When it is phosphorylated, it becomes inactive. So when the CDK has this phosphate group, it cannot act on the downstream pathways. And we know in the downstream pathways, which is active here, there are many things that is going to start the cell cycle. There are many events that is happening at a certain stage of the cell cycle, and they are induced by this key molecule, which is CDK. So until it is dephosphorylated by CDC25, which is a phosphatase, until this phosphate group is removed, it's going to stay inactive. This is why the passage from the active to inactive, inactive to active state is so sharp. So the graph, the activity graph of CDK doesn't go like this. Never. This is too sharp. This is too smooth. It should go this way. Hop, 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 hop. Active instantly, inactive instantly. And well, actually there are two different phosphorylations here, but for simplicity your book showed just one, and I'm going to do that also. So let's see the cyclin-Cdk, which is going to induce cell cycle. Checkpoints and how they are controlled. We have seen one control. It was cyclin. Cyclin is activated by transcription translation. And it is inactivated by degradation, by ubiquitination. Okay. And another level of control we know comes from this here, V1 inhibitory and CDC25 activatory. So V1 stops it and CDC25 activates it. Here this one is adding the phosphate group, and this one is removing the phosphate group. Okay. Again, this is not enough, because we know that this is the key molecule, and even a really few amount of this key molecule is activated, it is going to start the cell cycle. We have additional controls, like the inhibitor proteins. For example, here you see P21. They are binding in a post-translational way. They are different proteins, different polypeptides, but P27 can cover the surface of cyclin-Cdk, and it stops the activity. This way, cyclin-Cdk1, because its surface is covered, is not active anymore. And it's going to stay in this inactive form until P27 is removed. Okay? This is a transient way of stopping the cyclin-Cdk activity. Okay? Another way. And sometimes you have to delay the cell cycle. Remember, I said that maybe there is a mutation here. Where did I say it? Maybe there is a mutation detected here. The cell cycle should not advance until this mutation is repaired. So I said that it's going to wait, it is going to be postponed, it's going to wait for the DNA repair machinery. And how it is going to stop? Maybe because of this P27, which is blocking the surface. Okay. So everything we have seen so far is it was about the post-translational modifications, but some mechanisms also control it at the transcriptional level, which is actually kind of slower. So when the mitogen is received, and you know what mitogen is the extracellular signal which is inducing mitosis. It is taken by the receptor tyrosine kinase most of the time, and there are effector proteins. And these effector proteins can go into the nucleus, and in the nucleus they can act on transcription of some genes. So here in this case, some G1-CDK and some G1-SCDK, these are the two complexes that is working here. So they are working one after the other at close times. Okay. The effector proteins, they're going to activate G1-CDK and G1-SCDK, and what they do is that they are going to phosphorylate this RB protein. RB is retinoblastoma. Okay, normally the RB protein covers the transcription factor. You know, the transcription factors, they bind on the enhancers and they upregulate the transcription of some genes. And because this transcription factor is covered, it's not active anymore, as the G1-SCDK phosphorylates it, it becomes inactive by allosteric change, and transcription factor is set free. Now let's write it as a pathway. You have to get used to that. Mitogen is activating the receptor is activating the effector, the effector is activating G1-CDK and G1-SCDK, and G1-SCDK blocks retinoblastoma, and normally retinoblastoma blocks transcription of some genes required for the cell cycle. This way, by blocking the blocker, so here this is blocked, here this is blocked, by inhibiting the inhibitor, G1-SCDK sets free the transcription. Okay, this way some genes for transcription are synthesized. What can you need for transcription? For example, you're going to need DNA polymerase, you're going to need histone proteins, spindle apparatus formation, etc. Whatever you're going to need for cell cycle, they're going to be transcribed here. And we know there's a childhood disease. Check this unfortunate baby's eye. He or she has a tumor in one of the eyes. Because the retinoblastoma protein here, it is constantly inactive, which means this protein is not doing its job, which is blocking the transcription factors. It is inactive by default. Maybe the protein is truncated or something. And because this transcription factor is free all the time, it is transcribing these genes all the time, which means too much cell division, which means a tumor. So into this picture, we can add one more thing. Let's change the color to this. Retinoblastoma. Or let's say RB. Okay. And one last thing I'm going to talk about is P21. So P21, just like P27, is a molecule that is covering the surface of the cyclin-Cdk. So it is inactivating it. So let's start the story from the other end. We know that when there is a DNA damage, the cell cycle stops. So, this mutation or DNA damage blocks the cell cycle. But to be able to do that, first you have to understand there is a DNA damage. The DNA opponents, the mutations, etc., with the help of the DNA molecule itself and with the help of the histone proteins, it is communicated to a protein called p53. So this is a key molecule. We know that in several cancer types and several tumor types, p53 is mutant. Mutation of p53 is very dangerous. Normally, it detects the mutation and p53 is activated. When it is activated, it acts at the level of transcription. So this is not post-translational modification. This is transcriptional level. And it activates transcription of p21 gene. When the p21 gene is translated into a protein, it blocks the activity of cyclin-Cdk. Again, just like p27, it is going to block the activity. It is going to block the activity. So let's do it this way. Which is actually induced by p53, which is actually induced by DNA damage. And let's not forget the retinoblastoma here too. Okay, so if the DNA damage is in a repair mode, the p53 will be inactivated at one point because DNA damage is repaired, so the cell cycle can continue. So it's gonna stop, it's gonna wait some time, just like in the red lights, and then it will join. If the DNA damage is too big, if it cannot be repaired, it will not be able to pass through to the next stage. Anyway, this cell will not survive. Instead, it is going to suicide. Okay. So instead of activating the p53, it can also induce apoptosis, because if it is not in a repairable level, it's better if the cell dies instead. So this is a basic control of cell cycle, cyclin-Cdk complex. So these are the main pathways. Of course, it is much bigger than this, but if you're going to understand the cell cycle, you should know these basic levels.